Hello, my name is Dimitrios Glynos. I'm the Director of Product Security Services of Census. Census is the company that performs security assessments on devices, software, and infrastructure. And today we are going to explore how we can use program instrumentation to identify security bugs in software. So what's program instrumentation? Program instrumentation is a process where we add special instructions to a program in order to monitor, measure its performance, diagnose errors, or write trace information. So we imagine that if this is the normal program code, within our program code we add special instructions, instrumentation code, which allows us to measure things. So can we use instrumentation to identify security bugs? So what are security bugs? Security bugs are bugs that allow someone to terminate the execution of a program, to alter the execution, modify the execution of a program, or retrieve program secrets from program memory. And to help us in identifying automatically security bugs in software, we have program analysis. So program analysis is a method that allows us to automatically reason about program semantics. For example, is there a potential buffer overflow or a null pointer exception in this program? And because reasoning about such features of a program is sometimes hard, we can help this task through instrumentation. There are two main techniques in program analysis. There's static analysis and dynamic analysis. So in static analysis, we perform program analysis at a software, at a binary file or whatever, while it's not running, while it's sitting on the hard drive. Whereas in dynamic analysis, we perform an analysis on the software while this is executing. Now, let's see how we can use instrumentation to help program analysis identify security bugs. If we have access to the source code, then we can use annotations in our source code so that when we perform static analysis to the source code, we are going to get some early warnings about security defects. In the same manner, when we have access to the source code, we can compile in our software special instrumentation that may help us identify security bugs through dynamic analysis while we execute the software. Instrumenting a binary when we don't have access to the source code, when we have only access to the binary, instrumenting a binary and then performing static analysis is an area that hasn't been explored much, so I won't say much about this. However, we can certainly inject instrumentation in a binary where we don't have the source code for, and then use a static binary rewriting technique to inject this instrumentation in it and perform a dynamic analysis on the binary afterwards. Or we could leave the binary as it is and inject dynamically instrumentation in the program memory while the program is executing. This is dynamic binary instrumentation. We will see all these four techniques in today's presentation. So let's start with annotations. Imagine you are on your favorite IDE environment and you could annotate a specific function that, for example, this function bar should never receive arguments 1 and 3 as being null parameters. So in this way, when we run a static analyzer like CLANG analyzer on our software, CLANG can give us a warning saying that in this case here, where if P is null, if P is 0, then we call bar, and indeed P is passed as a parameter, as a third parameter in bar, and in this case we have a null pointer passed to this, and this was detected by the compiler, by the CLANG analyzer, because we gave this annotation here to our function. So we see how annotations in our program help the static analyzer or our compiler suite identify quickly security defects in the software while we're writing and compiling the software. Now let's see what we can do while we're compiling the software and adding instrumentation to it, when of course we have the source code for this. There's a very important project called Google Sanitizers, which is a special instrumentation you can add to an application. They terminate the application and report an issue when an undesired condition occurs. So we have a special sanitizer in this group of sanitizers called address sanitizer, which identifies memory corruption bugs with a very fine granularity, even if you do a 1 byte overwrite. We have the thread sanitizer, which identifies race conditions in our software. And there's also software which is available for not just normal programs, but also for kernel software. For example, the KC-SAN project, which identifies race conditions in the kernel. And there are other sanitizers in this Google Sanitizers project. As we said, these sanitizers allow us to do a very detailed root cause analysis. When we provide our program with some input that causes a crash, let's say that we provide some input to our program and we have an erroneous condition in the program. This condition is caught by the sanitizer. It identifies that this is a heap buffer overflow at a specific address. It says that this was caused by a write of 1 byte at a certain address. This was the code that led to this erroneous write. And this here is the chain of calls that created this memory resource where we wrote bytes after the end of this buffer. This is the chain of calls that created the actual buffer, and this is how we wrote 1 byte after the end of the buffer. And to do this, Address Sanitizer does some internal bookkeeping. It uses its own shadow memory, where it notes each change that is being performed in memory, and can identify, as we said, with a great granularity that there's 1 byte which was written over the end of the buffer. Now, okay, so the sanitizer will throw an exception. It will crash the program when it identifies this type of error. However, how do we drive the program into these interesting parts? We could use normal unit testing for this, or we could use fuzzing. So what is fuzzing? Fuzzing is a black box technique where you throw extraneous input into a program. You throw values that would cause the program to possibly malfunction, and you look if you have some exceptions ranged from the program. So once a fuzzer identifies that there was an exception raised by the program, it keeps the input file or the input it gave to the program and caused this exception. Now, there are 2 important features for fuzzers. The first one is coverage-driven fuzzing. In coverage-driven fuzzing, a fuzzer creates inputs that exercise as many paths as possible in the program. So it tries to work through all the if-then-else branches and tries to create test cases that cover, the whole program. Now, how do we gather these coverage statistics? This is gathered by injecting instrumentation into the program. This instrumentation can be injected at compile time, but it could also be injected at runtime. Now, there's also context-aware fuzzing. Imagine you had to fuzz Adobe Acrobat, and you provided Adobe Acrobat with a file with random input. When Adobe Acrobat would open this random file, it would not consider this to be a valid PDF file. It would not have the correct CRC signature at the end of the file. And so the Adobe Acrobat would immediately exit. It would not further process your file. In order to get more coverage, you understand that you have to use a fuzzer which creates input files that conform to the specification you want to fuzz. So you want a smart fuzzer which knows how to create files that look like a PDF file and only put random values in specific fields. And the same is true also for network protocols. So let's see an example of a fuzzer. where we are going to identify a security bug by injecting instrumentation into a program, address sanitizer instrumentation. We have a program called record parse, which parses binary records like this. There's this department header, which is a fixed size record. And then there's a series of person records in the file. Each person record is a variable size record, which consists of a fixed size part, which is the person header, and then a variable size part, which is the name. The number of bytes that are taken up by a name is defined through this name size field, which is part of this fixed size person header structure. So name size tells us how many bytes the name that follows occupies through inside this person structure. We are going to run our program with such a binary file. It will parse this file and tell us and print out, its contents. Now let's see how we can use a fuzzer to fuzz our parsing program and find security vulnerabilities in this. I'm going to compile my program by inserting the instrumentation of the address sanitizer project. So the way I do this is to add the fsanitize address option on GCC, and I get the record parse ASAN binary. Then I will also build another version of the program which contains both the ASAN instrumentation but also the instrumentation of my fuzzer, of AFL fuzzer. This instrumentation, as we said, will help the fuzzer understand how it's doing with coverage, how it's if it's creating input files that are going through all the branches. It gives us good coverage of the application. So this is the way to do this. I'm compiling with AFL GCC. I put fsanitize address here. And AFL GCC will throw in the instructions needed to also have coverage statistics in my binary. Okay, then we start AFL. This is the way to start AFL. Run AFL with an input directory that has innocuous files like the records database I showed you. I'm going to keep all my output files in this directory. In output, I'm going to give it this amount of memory, and I run my program normally. And this stanza here is the point where it's going to be replaced with the input files generated by the fuzzer. So with a make run, I run the fuzzer. So AFL begins. It's doing fuzzing, is creating these input files and tries to find crashes. And we already have 3 unique crashes up to this point in our fuzzing campaign. So I've saved one of these classes. I've named it AFL crash for you. Now, let's run the version of record parse with the address sanitizer enabled on the AFL crash file. We see that the address sanitizer has found a heap buffer overflow where there was a write of 8 bytes and there was an offending overwrite of 1 byte, which was 0 bytes after this memory area here, which was allocated through this code. What's really important to note here is that the instruction that made the offending write operation belongs to this line of code, record parse.c line 42. And this is the shadow memory layout where address sanitizer has marked that this is the 1 byte that was overwritten in error. So let's do some root cause analysis of this. We open the debugger with our normal program, and we put a breakpoint at record parse line 42. We run our program having as a parameter the crash file. Let's get some more context around in this code. So we see that it crashed in this file, in this line here. And let's see what are the conditions that caused this crash. Now, this structure here is of size 8 bytes. The memory which is allocated to P here comes from the addition, from the sum of this thing here. This is 1, so I'm not going to count this, and this portion here. Let's first print the second part. So this is a very big number. Our fuzzer created a file which had a record field which has this very big number. When this very big number was added to this number here, something magical happened. Let me show you what this value is. So this is 8 bytes. When we add 8 bytes to this value here, an overflow happens. The integer in this parameter here becomes 7, and malloc allocates 7 bytes of data. As we said, we are going to copy 8 bytes of data to previously allocated 7 bytes of data. So we have one buffer, we have 1 byte which creates an overflow. Now, is this only relevant for native code fuzzing? No. If you have instrumentation which you can, if you have coverage instrumentation, which you can throw to higher level language code like Go code or JavaScript code or Java code or .NET intermediate language code or Ruby code and so on, you can use projects like these to fuzz your programs. Your programs that are written in higher level languages. So there are projects like these that create special instrumentation so that you can fuzz programs in higher level languages. Now, we have these sanitizers, this special instrumentation that causes a crash when a memory corruption occurs. Could we use this in production binaries? The short answer is no, because the way that they instrument the program is too slow for it to run in production systems. However, there is special instrumentation you could use in order to protect an application from exploitation, from a security defect exploitation. For example, there's the canary stack protection, which you can enable with the fstack protector option in CLANG or GCC, that provides you with a canary value on the stack, which when overwritten will cause a crash to the program. So if you have a stack overflow, if you have like a buffer overflow on the stack, and your program detects that the canary value placed on the stack is overwritten, then it crashes your program rather than allowing the exploitation to continue. There's also control flow integrity, which is a newer feature which allows to crash a program if a function was called out of context. So if while exploiting a bug, the attacker manages to instruct the CPU to execute code which is already in memory in the program, but this is not a normal branch, nor not a normal not a normal instruction in the normal execution of the program, then this is detected and the crash is raised in the program. So this stops attacks like the return-oriented programming type of exploits. Now, there's also pointer authentication for ARM chips. This is a feature for ARM chips, where a program can crash if a pointer value is not created by the program itself, but is rather provided by an attacker. And you can enable this with these types of options. I'm now going to show you an example of how to use CFI to protect a binary. So we have a simple program here, which takes some arguments. And this program has a buffer overflow vulnerability. So when I provide it with some input, it crashes because of this buffer overflow vulnerability. Now, let's provide it with another payload. When I run this program with this parameter here, which provided a payload with specific bytes, what these bytes did was they exploited the buffer overflow vulnerability in the program and provided me with a shell. You see, this is a normal shell. I can do ls and whatever. So what I did was to redirect the execution of the program to a special point within the program that I could use to spawn a shell. This type of redirection in a program memory can be caught by CFI instrumentation. So let's see how we'll do that. We built the CFI instrumented binary like this. We use CLANG and fsanitize equals CFI, and we use a link time optimization. Okay. This is the binary that I produce in this way. If I provide to this binary the parameter I used before, then let's see what happens. So in this hardened binary, we see that execution stops with an illegal instruction exception when I try to redirect the code into the specific portion of the program that would provide me with a shell. So in this way, we stop redirection attacks that exploit vulnerabilities and execute code from which is already within the memory of the application. So up to now we had access to the source code. Let's see what happens when we don't have access to the source code. Let's say we have been delivered a third-party component, an object file or whatever, where we don't have access to the source code. Let's see, can we use instrumentation to find security bugs in this? As we said, one technique is static binary rewrite. With static binary rewrite, we inject instrumentation into the binary, and then we can go through some dynamic analysis and try to find through a coverage-guided fuzzer a security flaw, for example. Another thing to do would be, for example, to inject security controls like a stack canary into this third-party software that didn't have this type of security controls. I can do that with static binary rewrite. We can also reassemble the binary in a way so that its functions are at different points, and public exploits won't work on that because they won't know where each thing is in the binary. We can also add Google Sanitizer-like instrumentation to a binary that doesn't have this type of instrumentation and start fuzzing on that. So we see there are a lot of things that we can do with instrumentation on binaries, and to do this, you have to use software which does a very elaborate rewrite of the binary. It's not a trivial task to do this. And the good news is nowadays there are many frameworks that do this, and they have a growing support for different architectures like x86 and ARM and so on. So there are projects like MCSIMA, Miasm, Multiverse, and others. Dynamic binary instrumentation allows us to get all the benefits of binary instrumentation, but without touching the actual binary. So the instrumentation is injected into the program while it executes. And I believe the most popular software that does this is Valgrind. This is a software that carries ready-made recipes to detect many memory corruption errors, like also use after freeze, leaks, information leaks, and so on. There's also Dynamo Rio, which is a framework if you want to build your own dynamic instrumentation for binaries. There's also Intel Pin project, which is not which is not open source. However, it has excellent support for the Intel architecture. And this is all user space level injection. So we're injecting in the memory of the program while this program runs on the operating system. However, we could also be injecting instructions on a fake CPU, like we see in the AFL QEMU project, which runs the binary on a virtualization level and rewrites the instructions of the binary to inject the instrumentation. We are now going to see an example of how we can use Valgrind to detect an information leak. We have this little program here. We have this structure, a packet structure, which is not entirely initialized here. So we initialize some portions of it, but some other portions of it do not remain initialized. And when we send this packet over the network, the uninitialized part of this structure is going to leak internal memory contents over the wire. So let's see if this can be detected by Valgrind. As we said, Valgrind does dynamic binary instrumentation without changing, of course, the binary on disk, but changing the binary instructions while it's loaded in memory. So we'll run Valgrind with this. And we see that Valgrind identified that in the send to system call, there was a parameter which pointed to uninitialized bytes. So it detected the information leak here. And we can see the chain of calls, how it ended up into the offending system call. So to sum up, how can we use instrumentation within the software development lifecycle? So when we're doing development, we can use annotations to guide our static analyzers. The static analyzers we have, for example, available on our IDE environment. During testing, we can use dynamic analysis with instrumentation like the one we saw from the Google Sanitizer project to run our unit tests and identify at a very fine detail, at a very fine granularity, different security flaws like memory corruption flaws and so on, race conditions and so on. We can run focused fuzzing campaigns on our own components, on specific components that we're interested about because they're doing parsing or doing something else, which could lead to a security error. We could also run focused closed source component inspection, for example, for third-party components that we've integrated to our program using dynamic binary instrumentation, where we don't have to change the actual binary, we don't have to inject instrumentation to the actual binary. Now, in production systems, we can use instrumentation like stack canaries, pointer authentication, and CFI to protect our binaries from exploitation. This is, of course, also relevant not just for production systems, but also for production releases of binaries that would be given out to users and so on. If you'd like to know more about instrumentation, you can have a look at the two presentations we had performed have delivered at FOSSCOM in 2018, called Instrumentation with and Without Source Code. We go into a bit more detail on instrumentation and how this can be used even beyond security defect detection. For example, for measuring things in your application and so on. This is a very nice book. This fuzzing book is a very nice book on fuzzing, which explains all the principles of fuzzing. From hack to elaborate technique, this is a very good survey of the latest trends in binary rewriting. It provides many references to binary rewriting frameworks. And these are some links to software we've mentioned in this talk. That's the end of our presentation. Thank you for listening.
It's a great pleasure to have you with us today. And it was a great pleasure listening to your speech. It was highly technical, I have to say, but with many coding examples. But I'm sure that our audience, which are also highly technical expertise people, as well as I enjoyed it. I enjoyed it at least very much. Yeah, and I have to say, bugs have haunted developers since the beginning of time, and security-related bugs could lead to very serious problems in production systems. So I think that we can all relate to the issues that you mentioned, and they were very interesting. So, but you know, I mean, coming to this technology that you're introducing, the fuzzing, and I also wanted to mention pen testing, because I have read some articles regarding automated pen testing and integrating that into the CI/CD software lifecycle. Do you think that that there's going to be these type of tools that are going to emerge and become an integral part of the DevOps scene?
So let's say that they already have. There's a very big push for having these type of tools in QA testing right now, integrated into QA testing. A lot of our customers who are doing work with their customers, let's say in the United States, Australia and elsewhere, right now their customers are demanding that they see that they do perform some type of automated security testing during their QA cycles. And some of the work that we do is consulting work on how to tune this so that you can get the best value for the fuzzing time that you're doing in your infrastructure. So there's different types of testing you can do during QA. There's testing based on data on, let's say, a static database of known flaws that you can test your let's say web application against. Both ZAP proxy and burp proxy have modules for this to integrate into CI/CD. There's tools you can bind. There's workflows you can bind. There are fuzzing campaigns you can run and monitor these through your Circle CI or Jenkins software. There's, of course, as we said, Google Sanitizer type instrumentation you can build in your in the binaries that you're throwing to your unit testing, and you can also catch this and have this display on your ticketing system, and so that you can work on that, look at the root cause analysis, and open the relevant tickets on your backtracking system. So yes, this is something that right now is emerging. This is something which is becoming sort of a best practice. And we're seeing more and more work on this field, by the way.
That's great. So are you involved in that in your company? I mean, would you like to talk more about that? I think that the viewers are very interested to see a Greek company that is emerging on this topic, and you know, having services related to that, because there's a lot of need in the market, I think.
So what's happening is that we're asked to train in these type of technologies, companies, to consult on how they would better tune these type of technologies that they might already have. For example, we have customers who have deployed infrastructure for very large fuzzing campaigns, and they would like to know on how to better tune this infrastructure so that it finds bugs that are more, let's say, more intricate or more considered with more a bit of a business logic type of findings that are specific to their own targets. So one of the things we do is consulting on how to best tune these type of technologies. Another thing we do is focus training on how they can create processes in their QA testing to be able to use this type of tools.
That's excellent. I think it's a great area to be involved in, and there's a lot of growth, I think. And for Greek companies that do that, I think it's great. It's great. Very good. I have another question from the audience, and I hope if you guys have more questions, pop them in. The question goes, since some of those tests can be executed during runtime, could they also be easily automated in a live cloud environment?
So if live, we mean production, you shouldn't be doing any testing on your production. This is instrumented code. This code is slower. It's running slower than your actual code. You don't want to deliver services through slower code. Okay. You could have your staging or testing environment where you could instrument that, and through any way that you already have configured, catch the relevant exceptions and then do root cause analysis. So the answer is yes. You need to find the right instrumentation technology to be able to make this part of your application and then catch the relevant exceptions as you already did in your own unit tests. And if we're talking about instrumentation that protects code, yes, you can definitely use this, like the stack protection we mentioned, CFI we mentioned, or if you're deploying on an ARM platform on IoT, you can definitely use pointer authentication code to protect your software from the effects of exploitation. So in that case, you're not solving the bug that's there, but you're protecting the bug from being exploited. So this is a definitely yes, the definite yes for both higher level IoT platforms that run on an operating system, but also for lower level bare metal software, firmware, that you could have on IoT systems where you can harden this through instrumentation.
That's very interesting. Great. So, Dimitri, you've been in this area of the security sector of the business for many years. I mean, you're highly technical. What would you recommend to young, brave developers, in the Greek sector that are interested in security and want to explore, specializing in that area? What would you recommend to them?
So I would recommend two things, because each one is concerned with a different path. So if they would like to know more about security so that they build better code, better products, quality products, and so on, I would say that they follow the security trends. They take up on training in specific technologies that they're using. This could be web technologies. This could be the specific programming languages that they're using. What are the flaws that are very common to specific programming languages, and so on. And we also provide, as a company, we provide this type of trainings, of course. However, if they want to go into the path of becoming security auditors, then they should know that they already have an advantage because they are developers and they know how a stack works. So this is a very good thing. So what I would propose is that they would build also foundations on other two very important aspects. One of them being systems administration and networking skills, because these are very much needed if you want to do a proper audit of an application and being able to provide a realistic mitigation. And also work a bit on their systems development skills, low-level skills, so that they would be able to analyze anything at any granularity and so on. So these are two really important things if they want to go into security. Once they build these foundations, then they can follow whatever certification they like. There's many certifications out there for computer security. Others are more at infrastructure penetration testing. Others are aimed more at software security assessments and so on, and they can select the path that they feel it's best for them. Master's courses in cybersecurity do provide very good foundations for working in this field, and they explain why we use all of these type of technologies and why they're efficient in this type of work.
That's fantastic. Thank you so much, Dimitri, for all the useful information, all the great information that you provided to us today regarding security and coding, secure coding. We're looking forward to have you again on a future event and meet you in person as well. So we appreciate your coming. Thank you so much. Take care.
Thank you very much for having me. Good luck with the rest of the conference.